All right. Well, thank you very much. Thank you for organizing this session, and thanks everyone for joining us today. All right, so as Anna said, we are moving to very large scales in our universe, scales comparable with the largest visualized structures and even larger. And in my talk, I'll discuss basically LEM observations of intergalactic medium. Right, just to clarify what we mean with IGM here, well, pretty much everything that is outside R200 of galaxies and clusters, and this includes cosmic web filaments and galaxy cluster outskirts. All right. So in the background, I'm showing an image of a cosmic web from elastic stingy simulations, map provided by Tyler Nelson. And what you see here is emission from oxygen 8 ion that we aim to detect with LEM. So hopefully, we'll get these type of maps with LEM pretty easily. And here I show you LEM field of view. You see that it's actually pretty large. Even with just one pointing, we'll be able to probe a significant chunk of the cosmic web, at least on this scale. All right. So what can we detect, how we can detect, and what are the big questions that we may address with this detection? This is something I wanted to quickly go through today. And of course, everything I'm presenting on behalf of the LEM team and on behalf of the IGM working group. All right. Great. So wormhot intergalactic medium, let me start from there. What it is? Well, we know that about 40 to 50 baryons or regular matter at redshift below 2 is in this warm-hot phase, right? With the temperatures about 10 to the 5, 10 to the 7 Kelvin. Very low density, so typical number density of hydrogen is 10 to minus 7, 10 to minus 3 particles per cube centimeter, so quite extreme conditions. And we know that at least by redshift 0, by now, this gas is already enriched by star-forming galaxies through outflows. So the typical metallicities are 0.1, 0.3 of the solar. From simulations, we know that this warm-hot phase of the gas is actually filling space between galaxies. So it's basically tracing pretty nicely cosmic web. Why is it interesting? Well, one of the reasons why it is interesting is because we know that large fraction of matter in this warm-hot phase, and it is still not detected. So we have a big problem in astrophysics of missing baryons. All right, and if we detect mission here in the local universe, we can probably, uncover this mystery. All right, so how do we detect it? Well, with these densities, you can imagine emission is very weak, so it's really hard to detect it directly. Another difficulty is that it falls in extreme ultraviolet regime that could be quite heavily, absorbed and contaminated by ISM physics in our own galaxy. So probably going to soft X-ray is a better choice. And here I show a figure that shows prominent lines as a function of gas temperature. You already saw versions from other speakers. And we do see that there are quite strong lines of oxygen 7 and oxygen 8. There are also iron lines, particularly iron 17, which are not shown on this figure. But basically, this is what we want to look with LEM, right? And the question is why we want to do this. Well, there are a number of important questions. And here I just briefly highlight two very big questions that we want to address. The first one is where are the missing baryons in the low redshift universe? And for that, we need to detect and map WIN in the IGM. And the second question is, what are the physical processes that govern the evolution of galaxies, right? So this is a very broad question, but we should remember that detected IGM is an ultimate depository of gas that was ejected from star-forming galaxies throughout their lifetime. And if we detect and map metals in IGM, it would actually provide a very powerful characteristic to constrain our models of galaxy formation and evolution. The second question is also closely related to one of the Astra 2020 decadal priority survey area, in particular, unveiling the drivers of galaxy growth. So that's exciting. All right. What exactly we want to do? So now let's go to some specifics, and I will show you some preliminary simulations to convince you that we actually can see a lot of interesting stuff there. So the first problem we have is the problem of the Milky Way. Somebody already asked a question about this. So here I show a spectrum of the Milky Way in the energy range that then will be probing. We do see that there is a lot of prominent lines, also oxygen, 7, 8, iron 17, and others. So in order to overcome this problem, we need to select our filament observation specific redshifts to make sure that the oxygen and iron lines from the beam are falling in between these very prominent lines. And Maxim Markievich has done this estimation, and we basically found that the redshifts from 0.07 to 0.08, like if you find the filament in this redshift, it will give us all oxygen 7, oxygen 8, and some of the iron 17 lines. So in principle, we can avoid this problem of kind of decomposed emission from Milky Way and WIM, and of course, we need very high spectral resolution for this. All right, so now let's take cosmological simulations. We have plenty of them, and here we're using magnetic simulations from Klaus Dolak and his group. These simulations give us all the information about the electrical structure, and we are focusing on one particular filament, right? So this is how galaxies look at this filament. This is how density, gas density, and this is simulated X-ray emission within the LEM range, and it includes everything: X-ray emission, intrinsic X-ray emission from the filament, photonization, and cosmic X-ray background scattering, right? So this is how the same region will look in X-rays. So now, what we can do, the idea behind it is that we have a lot of optical surveys, right? And we can use these optical surveys to find where local concentrations of galaxies, and this would give us an idea where actually the filament is, right? And then we can point LEM there and get the redshift and try to detect WIM. So exactly the same thing we want to do in simulations. So we look at this region where we have local concentration of galaxies, and we map it with mosaic images with LEM, right? So 2 pi times 6 pointings, like 12 pointings in total within this area. And we try to extract WIM emission in these wide regions where we have the highest concentration of galaxies. Now, the issue here is that we have emission from galaxies as well, right? And we want to decompose emission from galaxies and emission from the WIM itself. So we identify all the galaxies, and we basically exclude halos of all the galaxies out to R200, right? Of course, it reduces the area about a factor of 2. The survey area is reduced to the result of that. So the question is, will we see anything from WIM? Well, let's look at the spectrum. This is a simulated spectrum from LEM, from this particular region over here, and dots show the spectrum itself, and the black curve shows a model of the Milky Way. It's a little bit difficult to see on the projector, but you can basically see that there are pretty strong deviations at some energies from the Milky Way itself. And these are our WIM signals that we will be looking at. So the signal from oxygen F is actually very significant, about A sigma detection, this is great. And we also see very strong signal from iron 17, 8 sigma, and 3 sigma detections. So this looks pretty exciting. Just if you're not yet convinced, you can look at the region of filament over here, exactly the same process we've done, and you clearly do not see any signal once we're off the filament. So no surprise. So this is pretty exciting because it means basically LEM will be able to observe cosmic web in emission. Besides emission, we can also look actually at absorption, right? And instead of looking at individual line of sight that Joe was talking about, this very common technique in ultraviolet, we can actually, account for the fact that within the LEM field of view, we'll be detecting a lot of X-ray background sources, all right? And angular resolution is actually pretty good. It's sufficient to resolve these individual sources. And this is just a simulation done by Maxim Markevich that also show within the LEM field of view, assuming 1 megasecond, this is how the cosmic X-ray background sources would look like. So if you detect that is half of the sources, we may expect that there will be about 2,000 counts in the 2 eV beam of LEM at 0.5 keV energy range, so quite a lot. So now we can detect actually, take the spectra from individual sources and combine them all together and try to look for absorption average over the entire large area field of view, right? So basically in the region where we have a filament, and see if there will be any absorption features. So this is the result of simulations. You can focus on here. Again, we are looking at the same region where we have high concentration of galaxies. And we see our spectrum that we're getting. And 2 interesting features are this one corresponding to oxygen 7 over here, and this feature over here corresponding to oxygen 8. Right, and you do see these 2 clear features beautifully in absorption, things are working. The second feature of oxygen 8 is a little bit weaker, but given that we will most likely know the redshift on the filament itself, we may still be able to detect it spectroscopically. And the same exercise, this figure, the second one, shows what we will see if we are off the filament, right? And you clearly do not see these absorption features. All right, with that, I wanted to go through a quick summary for this part of my talk. So I hope I convinced you that LEM is very powerful and it can detect a WIM both in emission and in absorption. So with emission, we are aiming to measure line emission per unit galaxy number density. And this characteristic itself will be directly compared with simulations when we use different models of galaxy evolution. And if we combine both LEM in emission and absorption, combining both, we could get some additional information on density of the IGM. How am I doing this time? 1 minute. All right, I have 1 minute, but I have the whole second part of the talk about additional science related to physics of galaxy cluster outskirts. I'm not going to talk much about it. There is this also kind of we have a lot of misinformation about cluster outskirts, and these are basically regions between large scale structure, between IGM and the central regions of clusters that have been studied pretty well with Chandra and XMM, right? So there is a huge, space to discover. And if you take the same simulations, last 15G, we can approximately estimate what can we do. And we basically, I show here a simulated spectrum from this particular region 8 between point R virial, half of virial radius and virial radius itself. And the red one shows the spectrum from the outskirts of clusters, and the black curve shows basically our Milky Way model. And you can see here that in outskirts, we can not only detect emission lines, but we can also look at a continuum, right? And this is pretty exciting because it means that you can measure velocities, abundances, do all the basic characteristics of these very complicated outer parts of clusters. And the questions we want to address, well, related to abundances. So we want to study what is the origin of heavy elements. We want to understand how the IGM was actually enriched. And we also want to constrain initial mass function. Basically, particularly the ratio of oxygen to iron measured could provide quite powerful constraints. Not going to talk much about it, happy to answer questions. The second thing we want to do, we want to basically measure how strong are motions in outskirts and how significant is the pressure created by these motions. Why this is important? Well, this is important because we know that this may bias our measurements of clustered masses through hydrostatic equilibrium, and this is very important for cosmology. So another big problem we may be able to solve, we see that the non-thermal pressure contribution is significantly larger in cluster outskirts, right? So our mass is significantly biased there. With that, I'm leaving here. This is just some preliminary results we've got when we type simulations of clusters, outskirts. We know exactly how the velocities and metallicity out there. We get the spectrum, we fit it, doing the same thing we're doing with observations, exactly the same thing like with Chandra or XMM. And we do find we recover basically correctly oxygen to iron, magnesium to iron ratios. And we even easily can distinguish the differences like factor of 5 for oxygen to iron, a factor of 3 magnesium to iron. So that's pretty powerful. And we also recover basically velocities that are consistent with the peak velocities over here in the true velocity distributions. So with that, I'm leaving you with some questions that we want to ask and address with LEM. Of course, there is more to come, but overall, I hope we convince you that LEM is uniquely positioned to address extremely challenging questions in astrophysics related to large structure in galaxy evolution, and some of them are related directly to Astro 2020 decade also. Thank you.